In this topic, we're going to be looking at how we would analyze data, and we're going to start that off by looking at types of data. By the conclusion of this lesson, we hope to be able to do the following things. Let's start by addressing our first goal, which is distinguishing between categorical and numerical data. Categorical data is usually descriptive and focuses on some sort of characteristic. If you surveyed people about their preferred operating system or their favorite Hollywood Chris, you would be collecting categorical data. It's useful for helping to understand your sample, but it's really tough to analyze. Numerical data is the bread and butter of statistics. It's data that can be counted or measured. Because it is numerical, it's a lot easier for us to analyze it using mathematical tools. Numerical data can be divided into subgroups of discrete data and continuous data. Discrete data is data that can be counted, and the values are always exact. Examples of this could include the number of passengers on a cruise ship, maximum number of players for a board game, or the number of bananas in a bunch. Continuous data, on the other hand, is data that can be measured. When you're measuring, the precision of your data values hinges on the accuracy of your measuring tool. And to that end, you'll never end up with exact values. We always lump continuous data into set ranges. Examples of quantities that would be measured using continuous data include the time taken to travel to school, the distance between individuals in line at the grocery store, and the height of children in a lower school class. Data collection is an important part of statistics, but being able to organize and analyze data is also a very valuable skill. Here I've presented an unordered data set of discrete numbers that were randomly generated. If I wanted to put this data in a format that would be easier to look at and analyze, I'm going to use a frequency table to do that. Frequency tables will show the value of my data, in this case these randomly generated numbers in the data set, alongside the frequency, so how often they occur within the data set. Depending on the size of the data set, it could be really easy for us to go through by hand and sort this data into a frequency table for later analysis. However, once your data set starts to get sufficiently large, you're probably going to want to use technology like your graphing display calculator or a spreadsheet program to make sure that you can sort and analyze that data easily. The visual representation of data in a frequency table is a column graph, probably one of the first types of graphs you ever learned how to make as a mathematician. In this graph, each column corresponds to one of the values of the numbers in my randomly generated data set, and the y-axis is telling me the frequency, so how often that number shows up in the data set. Discrete data could also be presented to us in a grouped fashion. The data that you see on your screen right now is actually COVID-19 summary statistics from Waterloo Region Public Health. And so I'm focusing specifically on some data that they've presented on their website that shows the number of cases sorted by age. From their data set, you can see how they've taken the positive cases in Waterloo Region and sorted them into age brackets that span 10 years at a time. These age brackets are referred to as class intervals, and for our purposes, we typically want those class intervals to be of equal width, meaning we want them to span the same range for each interval. Now, this data from Waterloo Region Public Health doesn't actually do that. Ideally, if we were to have collected and sorted this data as part of our math class, we would have sorted all of this data so that the cases were put into class intervals of width 10. So each range would have gone from 20 to 29, 30 to 39, 40 to 49, and so on, so spanning 10 years with each interval. The largest class interval in the data from Waterloo Region Public Health takes everyone from 80 and upward, and so that is potentially spanning 20 years or more in terms of the age of the patients who are in that group. Although this might skew our perception of the data somewhat, in reality, because this is such a high-risk age group, it's not entirely wrong to have clumped all those cases together. It is also worth noting that the original graph from Waterloo Region Public Health did not contain the number of cases written on it. That's a modification that I added to the graph. They just showed percentage of cases by age. But if this information was presented in a frequency table, we would actually be looking at the number of cases that corresponds with each age interval. Now, the information presented here is a bar graph. If we wanted to visualize it as a column graph, all we'd have to really do is rotate it. Although it's lacking a proper y-axis to show us the number of cases by age bracket, this is essentially the shape of what the column graph would look like. Continuous data can also be sorted into a frequency table, and we would also use class intervals for this purpose. The way the class intervals look is a little bit different because with continuous data, there's no gaps between the intervals. So our age brackets were not overlapping, whereas it looks like these class intervals are because it's showing weights instead of something that's discrete. Now here, if you look closely, you'll notice the inequalities showing the class intervals for continuous data have different inequality signs on either end. So these ranges are inclusive for the lower boundary. So if someone is 60 kilograms, they would be placed in the first class interval of this frequency table. However, if you weigh 65 kilograms, you would actually be moved into the next class interval. When we go to represent continuous data visually, we use the same style of graph as a column graph, except because it's continuous, we use what's called a frequency histogram. The main difference between a histogram and a column graph is that the bars actually have no gaps between them, again reflecting the fact that the data is continuous. As we continue our study of statistics, we're going to establish a variety of statistical measures that we can use to analyze a data set. The most common one that most people know about is called the mode. Now, the mode is the most frequently occurring data value in a data set. So from the random number generator from earlier, the mode was 2, because that was the most frequently occurring number. From the cases by age for COVID-19 in Waterloo Region, we would say, rather than there being one modal value, we might say that the modal class was the 50 to 59 age bracket, assuming we're discounting the 80 and up age bracket, which was a little over full based on the fact that the class interval wasn't the same width as all the others. The mode is probably one of the easier statistical measures to identify. You can do it by eye. It's just a matter of looking at the frequency table and seeing which data value has the highest frequency. As you start to spend more time looking at visualizations of data, you'll begin to notice that there are some common distributions of data that you're going to see. The first is a symmetric distribution. It's when the mode is roughly in the center of the data set and everything kind of tapers outward from there. It's got a sort of bell shape to it when you look at it. Negatively skewed data is another type of distribution you might end up seeing. That's when the mode happens on the upper end of your data set, and then you have a lot of values that skew towards the lower end, or in the direction of the negative x-axis. And so complementary to negatively skewed data, you could see a distribution that's positively skewed. That's when your mode is on the lower end of your data set, and you have a whole slew of values that skew towards the right or the positive x-axis. The final thing that I wanted to touch on very briefly today that we'll get into more detail later on is the notion of an outlier. So outliers are values that seem really far removed from the rest of your data set. Now sometimes these outliers are the result of measurement error, in which case they should be removed from your data set. In other circumstances, outliers are just really extreme values that belong in your data set. They're just somewhat irregular. And we can't always discount those values because they are still valid towards the statistical model, even if they seem well out of character from everything else that you're seeing. And so as we continue our learning and get some more statistical measures under our belts, we're going to talk about how you can actually identify outliers and begin to zero in on what you can do with them, if anything, as you're looking at a statistical model. Now that we have looked at identifying different types of data and looking at how we can sort it into tables, we are now ready to begin looking at how we can come up with statistical measures based on a data set. And so going forward, we're going to start talking about measures of central tendency and measures of dispersion. These are the calculations that are going to help us have a clear numerical sense of what's going on in our data sets.